All right, welcome to today's Accendo Reliability webinar. This is Fred Schenkelberg, and if our keep my fingers crossed, the power stays on and the interwebs gods shine brightly on us and allow us to continue. I think I've been doing this for over 100 months, and I've missed a couple of them because of technical problems. So hopefully that record is broken and we can start another 100 without any interruption. We'll see what happens. So today's topic came from a comment I got a couple months ago. And for the regulars, I recognize a handful of you that are routinely coming to the webinars, and I thank you. And for those that are new to the webinar, some over the different webinars I've done, I've talked about that doing testing just for the sake of doing testing was not all that useful or productive. And I often focus on a range of different reasons around testing, in reliability testing in particular, in order for it to have a lot of value. And so somebody asked me if I could elaborate on that a bit more, and that's the genesis for today's topic. I'm not going to talk about specific tests in particular. I might use a couple of examples, but the basic idea is that when we set out to do testing, we know that it's expensive and that it should make a difference. And so we're going to explore that a bit more as we go on. And I'm quite sure, and I know a handful of you, and I see a couple of new names on here, but the notion is that when we do testing, it should be on purpose or deliberate and for a specific desired outcome or purpose. And if it's not, then I really question why we're doing it, because it does take resources to do it. Now, in reliability engineering, we tend to focus on failures. Not exclusively. We like our products to work, and by definition, we're defining it oftentimes for our teams or with our teams as when it's working, it's got the absence of failures or a minimal number of failures over some duration. And so a lot of what we do, not just testing, but a lot of what we do is focusing on minimizing failures, whether it's degraded performance or just outright failure, or it doesn't start, or however we want to define what we call a failure. And so a lot of what we do, and testing is a part of that, includes sorting out, either discovering or understanding or characterizing failures, and so we can do something about it. Now, in doing that, it's expensive. Just, I know early on, I ran a accelerated test for some solder joints, a new solder joint configuration for a product we were making. And the question was, is it going to be reliable enough for our application? So we set up a design or a accelerated test, and it ended up costing between chamber time, which we owned, but it still took liquid nitrogen to cool it, and electricity to run it, and technicians to monitor it and maintain it, plus the samples, plus the test boards, plus the measurement systems. It was on the order of $100,000 to run what was essentially a pretty simple accelerated test. And the answer we got turned out to be well worth it, but the expense is right up front, and we don't really know what the answers are going to be. And so anytime we run a test, and some of you know it more acutely than others, is that, like, the price of the prototypes can be expensive. The price of the test facilities and equipment and jigs and so on that we set up is expensive, and so on and so on and so on. So even though that we're working for failures and understanding failures and so on, it costs us resources to do so. But if we do it well, and if we operate and conduct the appropriate experiments or tests, then we will actually create value. It will reduce uncertainty. It will create an ongoing understanding of a failure mechanism or phenomena. It will answer some question that is worth the expense and more. And that's what I mean by value. It returns a tangible benefit. And if it doesn't, once again, I'll probably say it way too many times here, then why do it? We have many other things we can be doing that actually make a difference. And so let's do that. Let's figure that part out. All right. So let me take a sip of water. I just got it. It's fresh out of the tap. And so why do we do reliability testing? What's your thoughts on this before I dive into some more of the topics there? And chat window is open. The Q&A tab I got open, and we'll watch that. But chat, I think everybody can see it when those come in. Demonstrate reliability goals. Yep, Nate, that's a good one. You could also use the Microsoft method and just ship it to customers and let them demonstrate it for you. Of course, I'm guessing Microsoft does an amazing amount of evaluations and studies and beta testing and so on, but they have a pretty complex set of products. Quantify quality over time. See, quality over time, I just call it reliability, but I get the idea there, Ken. Discovery, good. I like that term, David, is we figure out what's not working. We uncover those things that we didn't anticipate or know about. Estimate warranty life. Yeah. Okay. Yeah, I mean, there's between finding or uncovering failure mechanisms, what will fail, and how long before it fails are two areas that we do. And we have a whole range of different types of things that we usually get involved in: environmental testing, regulatory testing, standards-based testing, I think I said environmental functional testing. There's all kinds of ways that reliability testing, when we use the term reliability testing, we usually mean what will fail and when will it fail. But if we're doing environmental testing, will it work in these under these environmental stresses? We're also looking for, will it be okay there? We're trying to discover any weaknesses, those kinds of things. So I broadly define reliability testing as any time we expect it to work and we're evaluating or exploring, does it work or not work? And that can run from software prototype, hardware for the software team to work on. They expect it to work so they can run their software and do their development. Yet if they find a failure in software or hardware, that's still a piece of information that concerns reliability. So I broadly define what we mean by reliability testing. Now, some of the reasons, and I'll just mention a couple of them, and some of these are going to be repeats, is sometimes we just have to do it. It's a condition of sale. It's a condition to be in that market. It's, if you're going to sell a consumer electronics, consumer electronics product in the US, and it's going to plug into the wall, basically, most stores won't even carry your product unless it has a underwriter's laboratory seal on it, a UL certification. In some safety critical type systems, especially in Europe and Asia, they want TÜV. And I don't really know what TÜV stands for, but it's a regulatory body that evaluates products and safety and systems and how it's manufactured and evaluated. And it gives them, the customers expect it certified by TÜV, and TÜV naturally charges for that, but it's a condition of being in that market. Some parts of the world and some even counties within the US or local regulatory agencies will say, well, it has to be whatever. It has to have a screw entry. It has to be recyclable. It has to be whatever. But some will say, hey, it needs to be do no harm. It has to be safe for a variety of reasons or environmental reasons or whatever. So more and more regulations are impacting our products. Now, for me, I've stayed out of regulatory stuff as much as I possibly could because it rarely ever made much sense to me. One country would say it has to have these features, and another country will say it has other features that are not compatible with the other one. And that always kind of drove me nuts because neither one of them were actually related to safety or reliability or quality or anything else, but it was just something they wanted for a particular product or type of product. But these are the only reasons I know of that we just have to do it. It's just basically required or it's condition of sale. Now, if the excuse is, well, we always do it, and so we have to, now I don't buy that one. I draw the line there. I say, no, let's not do that test just because. Let's do that test either because it's, we won't be able to enter the market or sell this product unless we do it. I think that's a valid reason to do some kind of testing that we wouldn't otherwise do. But that's it. I don't think doing it just because is a very good reason. And I'm sure there's other reasons for that. Another broad category for doing testing is we have some uncertainty. We think this design fix will reduce the temperature to a particular degree and we won't have issues, with solder joints melting, for example, is a rough example. Or that this heat sink design that we're putting on this IGBT will be able to remove enough heat or disperse enough heat such that we don't burn out that component. Now, during the design process, we use engineering judgment and modeling and white papers and design guidelines and all kinds of things. And if we're not sure, if there's some sets of assumptions in there, testing is a really good idea then to go check that. One of my favorites was in there's a book about the design and development of the Boeing 777 aircraft. And it was the first aircraft with composite material for the wings. It wasn't aluminum, for example. And they weren't going to make 100 airplanes and go figure out if the wings worked. So they did a lot of modeling, a lot of testing, and a lot of characterization of the materials. And they built one wing and put it in a fixture that bent it, put a lot of a very deliberate amount of strain on it so that they could determine where it failed. How much could it take before it fractured? And then they used that to compare against all of their CAD modeling and material science modeling they were doing. And they found that the wing, as they designed it, was much stronger than they expected. And that was due to a bunch of cautious engineers going, well, we're going to add a little margin here. We're going to add some margin here just to make sure. And so they were able to verify a number of their assumptions in their modeling and adjust it to make some changes, but they were able to tangibly check. And it was a very clever, detailed type of test they were running for the specific purpose to say, we expect it to fail at this many foot-pounds, for example, this much pressure, or this much deflection, and we're going to go find out if it does. Much safer doing it in the lab than it is while it's flying, of course. Yeah, and you're right, Brian. There's groups that basically say, well, we expect this vibration in our stress relief features will mitigate or delay the fatigue failure type issues or so on. But that's an assumption in CAD, in experience and so on, but we go physically check it. And we can do that all over the place. So that's a good reason to do testing. And it helps by creating confirmation for models that we can use over and over again. Now, one point of warning here, just because it worked for your, composition of metal and joint that you have on this particular model of your vehicle, and you go change composition of your steel, for example, you go to a steel that's a little more pliable, it's not as brittle. Is your model still valid? How much of a change is too much of a change? And that's a slippery slope that many of us get caught in. Just because it worked with that polymer that we used last year doesn't mean it'll work with this new polymer that's 10 cents cheaper per pound that we're using today. So it's being very careful about what you're modeling and your verification. How far can that work? What's its scope that you can deal with? And too many failures I've run into as well. Well, it worked when it was a 4-pin connector, and it worked. Nobody complained when it was an 8-pin connector, but now we have a 16-pin connector with that same design, and nobody can seem to make it work, and it fails pretty quickly, and it cracks and all kinds of stuff. Usually that's a stack up of assumptions and not checking as you move beyond where the initial sets were just fine and were verified. So I run into that way too many times. Another one, and this is probably the biggest one, is we need to answer questions. Our development team and our management team and our customers and other stakeholders have questions. And a couple of you mentioned it, like estimate warranty life. So let's say we're going to offer a 2-year warranty. Well, the finance group would really be interested in, and so would anybody interested in profitability for many products, is, well, will the number of failures erode or eliminate any profitability? Because we're paying out warranty or replacing products or doing repairs on our own expense. If there's few enough failures, then our financial models and everything will work just fine. So we'll drive ahead with that. So it's a pretty common question. Another question is often seen near the end of a development program is it ready to ship? Or is it reliable enough that we can start shipping? Have we found enough of the defects and problems that are in this design so it's safe to ship? Those kinds of questions we may be running into. And that might be more than just one test. Another one I ran into years ago is where it was a US-based product, and they wanted to know, will it survive in the Amazon? Really hot and humid and a lot of moisture. And so they were really focused on an existing product that worked just fine for a number of years in the US. And they did a comparison between Houston area as far as humidity, for example, and the type of exposure that it would get in Brazil, northern Brazil. And it was dramatic. You would think it can't get much more hot and humid than Houston, but it certainly can. But one of the things they didn't anticipate, and we brought it up and asked about it, was insects and mold and fungus and stuff like that. When it's hot and humid on a long-term basis, and there's lots of active life around, some of that life likes to get inside of electronics and wreak havoc and cause problems. And so even though we were concerned about the set of stresses that we would find in the US, and we knew they would be slightly different when we moved to a different region of the world, there was also different stresses altogether that weren't really an issue where we're existing. And so beyond will it work in that new stress, will it work in these different sets of stresses? And that's a hard one to always keep in mind, is if you move from one region to another, what changes, what additional stresses or new stresses are going to appear? And so part of answering questions is making sure you're asking the right questions. That's usually a big part of it. And part of developing a reliability plan is the process of understanding, well, where do we want to go? What's our vision? What's our objective here? But then it's also, what are the things that could detract from us? Do we have any new components or new production facilities or new inventions that we're putting into this product? Are we working in environments that we don't fully characterize or have characterized? Do we understand all of the failure mechanisms or not? What are we going to do here? Part of it is asking the program manager, your experienced engineering team members, senior management, what questions do you need answered so that you can make the appropriate decision? And another big part of that is, well, when do you need to make that decision? That will influence your test planning pretty significantly. All right, so a big part is, let's ask the right questions, and the testing can help us answer those questions. We'll talk a little bit more about that as come up. All right, so let me flip this over. I mentioned doing it just because we've always done it as being a poor reason. What other ways is testing really not a good idea, or not a good reason, I would say, or a poor reason? Yeah, Brian, that's probably the most common one, is we always run it. And then I usually ask, does anybody look at it? Yeah, the pass fail ones, Neil, sometimes it's the technology or the nature of our failure mechanisms that's really the only deal. I think it's a last resort, but if it's just a standard and we got to pass, 77 samples have to pass. I actually got this question the other day. Well, if I do this test and 5 of them fail, should I just get 5 more units and see if they pass? And then I got my 77 and I'm good? No. Let's do the numbers here. Yeah, because the standard says so. Now, Karen, if somebody is requiring you to use that standard, either regulatory or a customer, well, then you got to do it. But if it's just a standard that seems to apply for your situation, it may or may not be relevant to anybody's question or need to know or understanding or reveal anything. Yeah, that is on the edge of that. It's more towards that, not a good reason. Yeah, I run into that a lot, Maximilian, is where folks are comfortable with what they've been doing because that used to work, or that worked, until it doesn't. And that's a hard part, is just because it worked on the last product doesn't mean that it's going to work on this product. We're designing a new product. It has differences in it. Yeah, lots of it's the same, but it could be different. Ignore the requirements. I've run into organizations that require a laundry list of testing. And I said, who uses any of this information? And what is it actually trying to evaluate? Or what are you learning from this stuff? And it was it's the list. We got to do the list. No, you don't. We can write our own requirements within the organization. If it's coming from a customer or a regulatory body, that's different. But if it's our own requirements, we got to do it. Yeah, the legacy tests, we've always done it this way. I want a ability to compare, and so on and so on. Those, when you peel them back a little bit, are really not all that useful. Now, in some cases, if it's the same technology, the same process, everything, the failure mechanisms the same of what you're looking for, and you're making improvements or design changes that should to change the performance, having the prior test to the current test makes sense. But all too often, and many of you have heard this story, where this test was run for about 12 years after this group changed their polymer so that that test would never fail. They had a product that was, or a polymer that was very close to the softening point of where the application was. And if they didn't process it correctly, it would melt in application. It would fail. But so they found another polymer that was a much higher temperature rated part, so that testing it at 200C was just never going to cause a problem. But they kept testing it daily for 12 years and never failed. And nobody ever asked, why are we doing this test? It cost them thousands and thousands and thousands of dollars over the years. Probably a lot more of that because they created a lot of expensive scrap too when they did it. So yeah, you got the idea. And when you run into one of these poor excuses, is, question it. Put some effort into understanding, is there really a reason to do this or not? Do the due diligence. And if there's not really a good reason, propose that you don't do that test and save those resources for things that are important, that you really do need to run. So how do you know if you're running a good test? Let's take a look at it that way for a moment or two. So one of them is when you finish the test, and this is one, I think why it was the pass fail was a poor reason to do a test, is that a binary result or a binomial type result out of a test, if we ran 77 samples and they all passed, therefore we must be good, is that it's, unless you've got a good characterization of your distributions that are involved with that particular failure mechanism, and you know that the stresses you're applying are representative or can be translated to use conditions in some way, just saying you passed a test doesn't really make a whole lot of sense. So for example, if you run, which is a super popular test in so many different industries, you take some samples, you put them in a chamber at 85C and at 85 relative humidity, and you run it for 168 hours, which happens to be a week, or 1,000 hours, which is a nice big 4-digit number, and you pass. So what? What does that translate to? Right now, if there's good understanding of that failure mechanism, and this is in that criteria is accelerated testing that accelerates your failure mechanism out to a meaningful distance in the future, then it can make sense. But if it's just run 85 for a week, what does that mean? What does that actually translate to in results? Okay, you pass the test, but so, if I do 3-point or a drop test, if I take my product and the standard says drop it 10 times randomly or 10 times, once per face and twice on the corner or something like that, it has some goofy set of criteria, and you drop it and it passes, the product's still working. Okay, so is your product bolted down to a desktop and it'll rarely, if ever, be dropped? Well, then it's probably too much of a good, we don't really need to know that. On the other hand, if I'm making a new portable device that we expect to get dropped multiple times per day, or my favorite product was that baggage tag scanner for the crews that load and unload aircraft, 10 times is just not enough to understand if it's going to survive in that environment where it's likely to be dropped 10 times per week easily. So if you're going to design a test, think through when you get done with the test, if you've got no failures, what does that mean? What is it? How do you know? How do you justify what that translates to? Or if you do have failures, what does that mean? Is that bad, or is that indicative, or is that what you were looking for? Is to find failures like in a HALT or discovery test. So as you design and set up a test, what are the scenarios that are the possible outcomes, and do all of those translate into something that is meaningful, that somebody actually can use to interpret, to say, okay, I can inform my decision making now. I understand those results. Now, it can do a lot of different things for us, right? It can, if we're verifying modeling, it may provide confirmation that our assumptions were correct, or that the model is close enough to reality that it's useful. So now that model is useful, but it also can reveal some nuances that may allow us to iterate the modeling to make it better or more extendable. So if I do solder joint testing on say a ball grid array, which I did years and years ago, if you design that test well and you change the package, say instead of I think I had a 258 ball grid array on this package, but we were going to expand it to 300 and some connections. Was this model that I'm using to calculate the strains that these joints would see still relevant when I make the package bigger? And then with a little bit of work, and we were able to show that the results we got were translatable up to some size of package. And then it started to break down. The size started to overcome the other assumptions we had on the model, or the knowledge we had in it. So if you can set up and run a test that characterizes a failure mechanism, now I'm on a step towards creating a physics of failure model, and I can avoid or minimize future testing. But if I run a very specific test for a specific feature or element of a product, and I'm not able to then model it or use it in a more generic way or in other circumstances, well, then it has less value. Characterization testing and characterization of a failure mechanism does take more energy and effort, but it pays off if you're going to be using a similar technology out into the future. So these are all very dependent on what you're trying to get out of this testing, this investment in the exercise, and what information is needed to make the decisions now and into the near future. So a good criteria is that it's going to be used by somebody to make a decision or a comparison, usually then to make a decision, or it allows us to get results that work now and into the future. Those are elements I would always look for in setting up a reliability test. And then timely. Some of you have heard me tell the story about the very first test I got. They wanted to know if this heating cable would work for 20 years in northern Italy. And I was like, well, I'll go to northern Italy for 20 years and I'll let you know. And they said, no, we need an answer in 6 months. And oh, okay. And then quickly figured out how you do accelerated testing. I wasn't even sure what it was called when I first started. But the idea was I needed to get enough of a answer that we could help the customer and our team say, yes, this product will have a low enough probability of failure out over 20 years. It will still generate enough heat to be useful to melting ice and snow on your bridges from now to 20 years from now. And so the race was we needed the answer in 6 months. And so if I would have delivered it in 7 months, the customer would have moved on, gone and found another solution, right? We would have killed that product. And if I got the answer in 2 years after the fact, again, it would be even less valuable. We're not making that product anymore. Why are you still testing it? Kind of thing. So part of reliability testing is it's got to create useful information. It's got to help support decision making. It's somewhere. It's got to be used in a very useful way or a valuable way. And two, it's got to be on time. You know, a test that's the results are a day late, you shouldn't have run that test. And as many of you know that have been in the lab, is not every test goes as expected. So you need to account for hiccups and delays and power outages and resets and accidents and so on. So always add a little margin into your test planning and number of samples if you can get them to account for all of those hiccups that occur. And the other, let's see, whoops, I think I went the wrong direction, right? Or did I repeat a slide? No, I got ahead of myself a little bit. Easy to interpret results. This one's not always easy. If I take a accelerated life test and I show you the plots of the 3 stresses and then the plot of the stresses versus time to failure graphic, that last graphic's pretty easy to interpret, but all the steps to get there, especially when it's a nonlinear pattern, the statistics can get pretty crazy. So working to create a result in that report that is useful by the person that needs that information. So it might be a Weibull plot, it might be another graphic, it might be a table, but understanding what they need to know and to what degree, how accurate does it need to be, how useful does it need to be, helps you then to craft the results in a way that they can readily use. Running a beautiful test and mucking up the results so that nobody understands it is less than useful, right? So that executive summary, the upfront, here's what the gist of this is, here's the results, here's the meaning of it, and so on, is the opposite of, here's the hypothesis, here's the analysis, here's the steps to run the test, here's all the equipment we use, here's all the derivation of the statistics that we did. And oh, by the way, in page 17, here's the results. No, make it easy for them. Put it all up front, and understanding what they want is the key to that. The other part is trade-off analysis. We did some evaluations of years ago. I was involved with a team. We were evaluating capacitors, and we're looking at, is there an appropriate adjustments we need to make to our derating guidelines? So how do we select the right sizing of voltages ratings for capacitors? And different technologies would respond to, say, temperature or voltage in different ways. And some were very insensitive to it, and you pick pretty much anything you wanted. And others were very sensitive. If we got close to the rated value, they would fail pretty quickly. And so in running the test, what we did is, instead of creating just a table, which you see so often with derating, is we created a graphic that said, as you increase the stress, here's the result on its expected lifetime. And it became very easy method to do the trade-off analysis. Well, I've got 2 rated capacitors. One's a little above our criteria, one's a little below the standard criteria. Is there much of a difference? If there's not, then I could pick the less expensive one. If there's a big difference, then I pick the more expensive one, for example. And it made it very easy for engineers to do those trade-off in the way the testing was reported to them. One of my favorites is that if you run the test to be all tests and you don't have to run a similar test for the next 5 years, just think of how much that saves, how many prototypes you now have available for other new areas that need evaluations or characterization. So when it's useful for the immediate purpose and decision, but it's also useful to avoid testing in the future. And that has a lot of value. It's not always easy to do, there's no doubt about it, but it adds a lot of value. So what else? What do you think? What other noticeable characteristics of a good reliability test? And don't say that it becomes a legacy test. I don't think that's a good characteristic. Yeah, Brian, you're exactly right. It's that you have failures. I didn't mention that, did I? I should have. And I know many of you heard me say it over and over again. You should have failures. It confirms that you're applying stresses in a meaningful way for the failure mechanism that you see, right? And maybe it's the one you wanted to see, and but it might be a new failure mechanism you didn't know about. But if it runs just to pass, it's unlikely you see failures. Simple and is inexpensive. Yeah, a lot of things, David, are done on bench tops. Or I had one client that needed a not a lot of temperature. And they needed to get up to like 40C, 45C for a particular test they wanted to do. And they didn't really want to spend the time or energy or rental expenses to get a chamber. So they cleaned out a broom closet, and the equipment that they were running generated enough heat that if you just kept the door closed, it would get to about 45, 50C pretty steadily. They also had to block they had a vent in there, so they blocked that. So it stayed pretty warm in there. And it was just, the expense was figuring out where to put the mops and brooms that they pulled out of the closet. Yeah, good correlation. That, is a tough one, because sometimes we just don't have that information from the field. And in some cases we do. In some cases we get really good information back. But over time, it's great when we can confirm that. And it's even better if we can do it early in the program. So if we can run some extended beta testing, for example, and get really good information about that. This one's tough. I've even gotten into some companies to do buybacks. We're going to replace your product that you've had for 5 years with the same product, so that we can take it apart to see how it's aging and then see if it met our models. Now, that was an expensive program, but it sure generated a lot of useful information for us. Yeah. Good. All good. All right. Let's see. I got to actually get back to my slides here. There we go. Now, here's a couple of notes of what I think are the best reliability testing that we can do. And the first one may surprise you, is just don't do it. I look at testing as a last resort. There are deliberate, rational reasons to do testing. And all too often, like one organization I worked with, they had, every time there was a field failure, a significant field failure of some sort or another, either from design or from the suppliers or from the manufacturing process, they would add a new test to the next product development cycle. And so they have up to like 48 different tests they always ran. And it was a long checklist, and it was just a scramble to get all these prototypes through all these different exercises they did. Vast majority were things that were completely designed out of the product. And so of course they weren't going to fail. And so vast majority of those tests really did not add any value, except it set a criteria for the designer not to go back to this other practice or fall back into an older solution. But they could put that in a guideline. They could do all kinds of things rather than testing. And so we made the argument, let's take out this 20 of these that really have no basis anymore. There's little to no rest that anything's going to happen with these. Let's take those out, because you've passed this test for the last 15 cycles of your product development. You're just not going there anymore. And that alone saved them like $1 million a year. And then we pulled out another 10 of them saying, these are low risk. Given your development process, the experience of the engineers, everything else, these just don't make sense. And they're redundant with some of the other things you're doing. But let's keep these other 10, because they actually are going to provide value, right? But we were able to get rid of, 35 or so of these tests, which they never missed. Didn't need to do them. It freed up so much resources, and they were able to double down on the ones that really needed more samples or more time, and they had it to do it. So it gave them way more value for a lot less cost than that we're doing. So if the right decision is, let's not do this test, there's a lot of value in doing that and just not doing that test. Now, you're going to get people that are going to be nervous. We've always done this. We've always like, what have you actually tangibly learned from those tests? Yeah, exactly, Brian, is make sure that what you're doing is actually going to be, one, used, and it's actually useful. It's on time, and it's accurate, and it's meaningful, and it helps somebody that has a question get information so they can make a good decision. And just doing it because is not one of those reasons. So just don't do those tests is my advice. The other piece of this, in order to make a really good reliability test plan, is really understanding that you need to answer the right questions. All right. So by talking to the rest of that team, and what decisions are you going to make, and what is the critical information that will help you make the right decision, right? If I have vendor A and vendor B, and they're going to say same form, fit, and function, right? Or slightly different solutions. We can do modeling, we can do analysis, but if we don't have good reliability information and we know that that's critical to the decision, well, then there's a reason to do a test, to go do a reliability test. Which one's more reliable? Now, part of that is, any of you that have done a hypothesis test know that how much of a difference matters. So how much more reliable does vendor A have to be than vendor B for us to say, well, it doesn't matter, they're both about the same? So is it plus or minus 2 months, or is it plus or minus 2 years? What's the precision that we're looking for in this comparison? Because determining which one is better or worse statistically significantly to within 2 months is much more difficult and more expensive than if it's plus or minus a year or so, or 2 years. For example, if there's a large difference between them, it's easier for us to detect that. But also, if we design a test that's counting on that difference, and they're really within a couple of months of each other, that'll show that they're about the same. Now, those two results, one is clearly better than the other one by a significant margin, is informative to that decision maker. But also, what are we giving up? How much of a difference makes a difference? So if the failure rate is 1/10 different, it'll take us 400 years to cover the price difference that these two vendors have. If they create a 1% defect rate versus the other one, it only take a couple of months to pay for the difference. So part of what we're trying to understand is not just is one better than the other, is in that test design, how well do we need to know that? How precisely do we need to know that? What is the business ramification? Because we're trading off deliverability. Can they get the parts to us? Will they continue to make them for the next 10 years? What's the quality of their product? How consistent is their production process? And cost. And if we're not creating a test result that is useful in making that trade-off analysis, then we've missed the point. Just saying one's better than the other may not be enough information in order to make the right decision. So we need to understand that. Sometimes we need to really sit back and go, are we measuring the right thing? Are we able to measure the right thing in this test? Right? Some products have built-in self-tests and other products don't. And how do we know it's working or not? If we have a mechanical system, is it a destructive test to look at load ability for it to withstand a load, or are we looking for tensile strength and it's a destructive test? Are we able to measure what we're trying to evaluate well enough? And so measurement system analysis allows us to make sure that what we're testing actually helps us get a clear understanding of what's really happening, and that we're not just doing a random number generator because we're using the wrong system to make the measurement. And so by diving into what questions need to be answered, what questions need better information, and then how much better and how accurately, and are our systems accurate? Are our vendor systems accurate? It's not enough to say, show me the data. Well, what's the measurement error on that? Right? How inaccurate is each of those numbers? And we need to account for that. So a lot of what we do relies on not just the presenting question, but how well do we need to answer that question in order for it to be a really, really useful test. And then it should make a difference, right? In different ways of doing that. It's not just that it discovers a failure mechanism, so I'm saying here exposes a weakness, but it could remove uncertainty. If we have a new component and the vendor says, well, it should last 8 years, but we have a 10-year expected life on this product, well, that's kind of fuzzy. And what's the vendor saying is the definitive it should last? Does that mean 50% of them will last 8 years, or is that 0.5% will let or we'll have a failure rate of 0.5% at 5 years? If we just don't know and we're not getting good information from the vendor that we can trust, well, running a reliability test that gives us a time to failure distribution where we can say, all right, at 8 years, we're going to have a 0.5% chance of failure. And at 10 years, we're going to have a 1% chance of failure. Now we can make a decision. Let's go figure out what's the cost per failure and sort out what's the right answer here. Now, sometimes what we do is we're trying to, for example, the risk of a product delay. And I think most of you, many of the folks I know have had the experience where you're in the development program and then one of the last minute tests that we're just wrapping up finds a big problem. And it's a hard decision. Do we delay the program and fix this and there's other things that we can, or do we launch and fix it as we go? Or do we launch and fix it on the next iteration? Depending on the magnitude and understanding of what failed that is perceived as a big problem and how big it is, will inform that decision. But let's say we want to really want to launch on time. It's for the holiday season. It's for a big conference that we want to introduce it at, or trade show or whatever. But there's a risk that we won't find something until late in the program, so it fails. It delays the program. It might not happen every time, but there's some risk, some uncertainty that it could. So let's run some halt tests. Let's run some evaluations earlier. Let's argue that getting those first prototypes into areas where we can explore what could fail gives us time to fix those things without delaying the program. And that's a common argument for halt or for discovery testing or margin testing, to do it earlier. But you have to quantify, well, what's the cost of delaying the program? Now, one team I worked on was Inkjet Printer. They had like 50 people working on the development of this. Every day delayed cost the lab $1 million for facilities, for management, for headcount, for equipment, and everything else they had. And the program manager says, yeah, if we delay a day, it costs us $1 million just to run the lab to deal with this issue, rather than moving off to other products, doing what we should be doing. And so it was a way for us to quantify the impact of a delay. And so if it was delayed for just a week, it more than paid for all the prototypes we ever wanted to do halt early in the program. And so that became a very easy argument to run these different kinds of evaluations early in the program to find all those things that we would otherwise find late and cause problems for the program's launch. So if what we're doing doesn't make a difference, well, then it has very little or no value. So if you can connect it to what is not just that it provides information, but that it helps people make better decisions, that it helps people choose the right vendor, it helps people actually design a product that works better. If we can quantify those differences, that's value. That's where we really run into making a difference. It goes to the bottom line, it goes to the availability of your equipment, it goes to customer satisfaction, and so on and so on. But we need to quantify it in order for us to really build on that credibility. We're doing the right testing because they make a difference, they add value. So those are some of the key things I think are critical to doing testing well. And there's lots of different options for this depending on your organization, but it's something to keep in mind. Well, I've said it, I don't know how many times so far. If it doesn't matter, don't do it, kind of thing. And so this might be just a rhetorical test for you, or a rhetorical question for you, but can you honestly say that for every test that you've got coming up for your product or product lines, that you know how much value it's likely to create? And for the ones you've done, how much value did they create, right? What difference did it really make? And a simple example is run Halt. And I found 5 things that the design team said, oh, we need to fix those. Each of those will cause, X% of failure rate if we don't solve those or minimize them. Well, if you just take that extra step and say, oh, that's great. We did this prototype. We ran 2 of your samples or 4 of your units through this. We found these 5 issues. You solve those. That change in failure rate translates to the Y value of what's my cost per failure, what's the percent, how many units are we shipping times that failure rate times the cost per failure. Run it out to what's the dollar amount that test actually helped you to solve, or to capture, to what value did it create. But creating a portfolio of those things, this test makes a difference. Helps you to get the feedback you need as you design and build and manage and run reliability testing, so that you get sharper and keener at which ones make a difference and which ones add value for a particular circumstance. And that allows you then to really get the feedback you need in order to make the right recommendations, to design and build tests that actually do create value versus don't. And so that's a key part of this whole process, is get the feedback you need. All right, so that's I think my last slide's there. And I've got a couple of minutes, so I'll take a look at the comments and questions, and hopefully this reinforced the idea that let's do this stuff on purpose. Let's do it deliberately. All right. Well, I'll stay on the line. If there's any comments or questions, I'm always happy to chat about anything that's on your mind. If you have any ideas for future webinars, we got those coming up. I did get a request yesterday. So I already, and now I've drawn a complete blank what it is. I've been focusing on this presentation. Coming up for next month, I should have that up and available to sign on shortly. And I'll keep an eye on the chat. So for those that were able to join live today, thanks so much. And thanks for the participation in the chat window. And so I'll wrap up the recording here. It should be out in the day or so. Hopefully our power stays on. And it'll be available if you want to share this with anybody. That's great. You should be able to find a good link for you. And if there's anything else, just let me know. So I'm going to go ahead and stop the recording, and then I'll keep on the line as long as there's some questions or comments, and I'll address those just in a moment.